We have an assignment and a fine transformation. So the previous layer, we have these expressions for the previous nodes. We apply the fine transformation. This just means we plug in whatever expression we had from the previous layer and we continue. It will make more sense with the example if it's confusing for now. Just bear with me 1 second. For the values, there are 3 options. So this is our node before the value, and we apply the value. This is after the value. And there are 3 cases. Either the lower bound here, the concrete lower bound, well, the actual lower bound of the abstraction is always in greater or equal than 0. Then this is the identity function. So whatever we had before remains the same. The other easy case is when the upper bound is smaller or equal than 0. Then everything is set to 0, including the symbolic expression. The in-between case is where the lower bound is reset to 0, the upper bound remains the same. This is the undetermined case in a sense. And now we create a new symbolic expression that represents the value in subsequent layers. I'll show the example. So here at the beginning, we just have 0, 1 as before, plus a symbolic variable representing the index. At the first layer, nothing changes much. The expression is just whatever a fine transformation does this layer here. The range is the same as we have computed before. What changes is at the next layer. You see this is x20. x20 is 2 times x10 plus 3 times x11 plus 0. And instead of putting x10, now we put the linear expression that is represented by x10. So we're going to have 2 times this, plus 3 times this, and so on. So now we have an expression that represents the value of x20 with respect to the values of the inputs. And the advantage is basically if you have things like, let me see if I can go, okay, I'll write here, hopefully you can see. Let's say you have an expression at some point where you do x minus x. Okay, this is as value 0 normally. But now let's say that your x has values minus 1, 1. Okay. Now when you do minus 1, 1, minus 1, 1. This is basically why it's basically a plus, whatever. So what you get to is basically minus 2, 2. So you get a much larger interval than the actual value, which is 0. So this is the problem with the interval domain. And so what these linear expressions are doing are basically, whenever you have something like this cancels out without having to do the interval evaluation. And so you get more precise ranges. In this particular case, it doesn't help. Where it helps is down here. Before it was something like 0, 3 in the previous with intervals, and now we get something smaller, which is 1, 2. And so at the end, when we evaluate the outputs, now we get the range to 8 for dogs and minus 1 and 1 for cats. And you see that the range is for x30 is always bigger than the range for x31. So here we have proven the point. Yeah.
The symbolic evaluation part to reduce the intervals definitely makes sense. I'm curious, the previous method that did not work seemed very dependent on how much we're perturbing things and sort of what the tolerance of that neighborhood of the
I think all of these abstractions are.
Okay.
Yeah, so it's orthogonal to the abstraction that we use.
So in a network with like millions and millions of layers and things like that, are we able to make this like memory efficient enough to work, or is that still open?
No, you can actually. When you have larger networks, the main problem is that you're not going to be as precise. But there are ways actually you can do all these operations as matrix multiplications and all that. So it's all easy to do in a sense. The main problem is the precision. Even with this symbolic propagation of expressions, it's not going to be very precise for large models. You need something more. Okay. Okay, I'll bother you for a second with a modified example. Now we add an extra layer because I want to introduce another abstraction. This one already works here, so I have to make it not work. So we continue with an extra layer. So now we stop where we were before, so x30 and x31. But now we have one more operation to do. So here we have to actually apply now a value. And you see that the range is -1, 1, so we have to actually introduce a new symbolic expression that represents this value here. Now when we get to the next layer, you see that x31 appears in the expression of x40 and also in x41. And now the ranges are again overlapping and we have a false alarm. So this is my excuse for introducing another abstraction. The problem with doing this basically is that we are losing any relationship with the input. And so what this abstraction is trying to do is keep still, even when the values are undetermined, try to keep some relationship with the input so we can still have this cancellation effect. So what the deep poly domain does is instead of keeping one single expression, symbolic expression, it keeps two. So it's going to be a symbolic lower bound and a symbolic upper bound, plus the actual abstract, concrete, I call them concrete, but these are actual numbers, A and B, actual lower bound. So we have the numerical lower bounds and the symbolic lower and upper bounds. And so for the values now, we have in fact 4 cases. Essentially the idea is that whenever, for each neuron, we have this lines bounding their values. So we're going to have lower bound and upper bound, symbolic, lower bound and upper bound numbers. If the value is always active, this is the identity function. If it's inactive, it's everything goes set to 0. If it's not determined, we have these 2 cases. So essentially, you see this red shaded area here. This is the most precise convex approximation of the value. Now here what we want is to keep only 2, so this is a triangle, we just want to keep 2 of the constraints in this triangle. And how we choose them is basically by the way the constraints that minimize the size of this region here. So in the first case, it's when the lower and upper bounds, the numerical lower and upper bounds, are sort of centered around 0. In this case, we keep this triangle approximation, so the upper bound is going to be this line here, and the lower bound is going to be 0, this line here. The other case is when the bounds are a bit not centered, so a bit shifted from the left or the right. And now the upper bound is the same as before, but now the lower bound is this one, other side of the triangle instead of this one. So it's the lower bound is going to be x. So this is the difference between these 2 cases. For some technical reason, here we can reset the lower bound, numerical lower bound to 0. Here we cannot because we want the bounds to always, the numerical bounds to always be bigger than the other symbolic bounds. But in fact, it doesn't really matter. We don't really use the numerical bounds after the value, so it makes no difference. I'll show the example. So this is the example modified to have this extra layer here. The ones that the symbolic domain was not able to verify. So here, at the beginning, nothing different happens. We still have this 0, 1 intervals, these symbolic expressions for the lower and upper bounds. At the first layer, we sort of duplicate, if you want. We have the same symbolic expressions as the symbolic domain, but now it's duplicated because we have, the 2 bounds. We still evaluate the intervals in the same way, except that now this one gives us a value for the lower bound, this one gives a value for the upper bound. Let me get to the interesting part, to this point here. So here we have x30 and x31. You see, this is where the ReLU actually makes a difference. So here we have the range -1, 1. So this was problematic before. This is where we introduced the symbolic variable for x31, and we lost the connection to the input. Here now we have this abstraction instead of the ReLU, so we do have a symbolic expression that depends on x31 before we apply the ReLU. So I'm using the same name, but this is x31 before the ReLU, which depends on x20, x31, which depends on x10, and so on. So there is still a connection to the input. And now I'll show you how we actually use these connections to compute the bounds. So when we get to x40, we have this expression here. Now we have to basically back substitute all the expressions to the input to actually find the value for the evaluated range of the values. So here we have x40. These are all the expressions that we collected from before. So now we have a symbolic lower bound and symbolic upper bound. Now we have to replace x30 and x31 in the two instances of the expression with the right expression from the previous layer. And this depends on their coefficient. So here we are in a lower bound. We have a positive coefficient, so we're going to replace this x30 with the lower bound of x30. Here we are in the lower bound, but we have a negative coefficient, so we're going to replace it with the upper bound of x30. And like that. Continue like that. So if we do that, we're going to have this expression now, which depends on the previous layer. We're going to do the same matching with the right expression. We get now to the first layer, and then we get to the input. At the input now we can replace with the actual intervals, and we get this interval 2, 5. With symbolic domain we have the interval 0, 5. Now we're doing this until the input. We actually can do a partial back substitution. It's just going to be a bit less precise. So we can stop, in fact, anywhere in this back substitution process and get an interval that is a bit larger. So if we stop at the first layer instead of going to the input, we're going to have a range 1, 5. We stop at the second layer, it's going to be 2, 5.5. And the layer even before, we get the worst bound 0, 5. And it's not obvious that going further back is going to improve necessarily. So for instance here, we make the lower bound worse, but the upper bound gets better. So when you get to the input, it's obviously the best bound that you can get. Anything in between, there isn't a rule on how far you get and how precise you get. It's not direct. Okay, good. So here we get 2, 5. Now we have to do the same for x41. We have to do all the back substitution. We get the range 0, 1, which is good. We can prove now the property. The range 0, 1 is always smaller than the range 2, 5. If you noticed, we have done this back substitution to the input. So we always have to maintain basically expression with respect to the previous layer and then substitute everything. It's a natural question to ask, what happens if we actually always keep the bounds with respect to the input? So we always do the substitution right away. So I'll show you an example. It actually gets worse. So doing the back substitution is costly, but it's what gets the best results. So here, if we do the substitutions, in this example here, we're going to have, for x10, we apply the ReLU. And now we do the substitution with these expressions. This gives us this expression here, and same for x11. Now we have this expression. So we always try to do the substitution to maintain an expression with respect to the inputs. If we continue, here we would have these expressions normally. If we do the substitution, we get these other ones. What gets worse is afterwards, when we get to this layer here. At this layer here, we have, normally we would have this expression. Doing back substitution, we actually would get this range here, 1, 5.5. If we do the whole substitution right away, and with the substitution that we maintain during the analysis, we get actually a worse range, which is 1, 6. And you would think, okay, it's not too bad, we lose just a little bit. In fact, it gets even worse afterwards. With one extra layer, we get minus 1, 6, which is very large. We get a worse lower bound and a worse upper bound, and with the back substitution we actually would have gotten 1/4. So doing this whole back substitution thing is worth it because we get actually worse bound if you do it like this. Okay, in fact there are many more abstractions that people have proposed. I just mentioned one other option, which is, so far I showed you abstractions that only abstract values by one. In fact, you can get more precise if you abstract values together in a way. So if you have the input shape here, if you do one, you abstract one value at a time, you get this abstraction. If you abstract them together, you actually get this smaller abstraction. So you can actually get more precise. Okay, how we implement this? Well, in fact, they're quite easy to do. So you could actually try them as an example for yourself. I just wanted to then mention roughly, so we talked about prediction stability. I want to mention the option of doing other kind of stability verification, because prediction stability is not necessarily not necessarily a good property, in fact. So here there is an image of an 8. This is the NIST data set, for those that know it. And we train the standard model on it, nothing fancy. If you actually modify the brightness of this image to make it even not recognizable at the moment, it's still classified as an 8. So just showing that whatever perturbation you have still classified in the same way is not necessarily a good criteria. So another option is to look at how stable is the explanation for the prediction in a way. So one form of explanations to use saliency maps, for instance. So these are essentially the gradients of the input with respect to the outputs. So essentially, if you do this, this is an image of a dog. Now, if you go, you compute the saliency map, you basically have these pixels highlighted. So these are the pixels that are more impactful in a way. They have more impact on the classification of this image as a dog. So now you can imagine that you could do a sort of a saliency map stability verification problem where you have your image, you have the saliency map corresponding to the image, and you have a sort of an expected saliency map. You have, depending on the transformation, let's say you just change the brightness, you expect that the important pixels or the reason for why the image is classified this way are roughly in the same place. There possibly are fewer of them, but you have a sort of an expectation on the saliency map, and then you can compute the distance between the actual saliency map of the image that you obtain with the perturbation and the expected one. And if you notice here, if you actually look at the saliency map of the image from around this point here, right, you don't recognize the 8 anymore. So you could argue that beyond this point here, the reasons for why the image is classified as an 8 are not valid anymore. So this is unstable, and this one here, we have stability of the prediction and the explanation. So if you are curious about this, you could look into this paper. No, not the paper. Okay, now we get to the safety part. So here we just really do, so stability was one instance of a safety property, now we do general safety properties. And as a typical use case, we can consider this ACAS XU dataset. So these are, it's a system for collision avoidance of drones, effectively. And what they have done was to try, so the actual system is implemented as a gigantic lookup table that takes up several gigabytes of memory. What they have tried to do is to approximate it using a surrogate model, essentially 45 surrogate models, which are 45 radar networks that they take as inputs 5 sensor measurements, which compute the distance between the drone and another drone, or the angle, or these kind of things. And then they give these horizontal advisories to the drone, saying, okay, you have to turn right or left more or less strongly. And in some paper, talking with the experts on the systems, they actually have come up with some properties of the systems, this neural network. And properties are of the kind, okay, if the intruder is near and approaching from the left, then you should go from right, this kind of thing. So essentially you have your sensor measurements, you have some ranges or some properties, some specification on their values, and you have an expected output that you have in the simulations. So how we do the static analysis? Again, we formalize the property first, and then we do the static analysis. So here, more generally, we're going to have an input specification and an output specification, and simply, our property is going to be the set of traces that satisfy this input specification. So the input of my trace, whatever is fed to the neural network, satisfies my input specification, and the classification satisfies my output specification. I'll give you another example. Here, let's say we have two inputs, two sensors, and we can only have as output clear of conflict or strong turn. And let's say they have this constraint on, I don't know what is this, the speed or the angle or whatever, it doesn't matter. And these are the constraints in the input, and in this case, we are clear of conflict. Let's say this is what we want to prove. So, what do we need for the semantics, in your opinion? Well, in fact, the same as before. We can still stay with the prefixes semantics. So we still have the same situation as before. The case that we've seen before with the local stability is just a particular case. So we can still work in the same way. So in fact, the abstraction is going to work in the same way as well. So we're going to have now an abstraction of the input specification, and we're going to obtain an abstraction of the output and see if it works, if it's included in our output specification or not. So in fact, we can use the same domains as before, but I just wanted to show you how they're not always, like we have seen before, that this deep poly domain was the most precise one that we have, but it's not always the case. So I'll show you in this example here. So now this is the example we have seen before. These are the input specification. What we expect is that we have a clear conflict. Now this is deep poly, right? So we have the two symbolic lower and upper bounds, the two numerical lower and upper bounds, and now we do the analysis. At the first layer, we already have to do some radial abstraction. So we actually, in this case, the bounds are not symmetric with respect to 0. So we use this abstraction here, this triangle abstraction, which gives us this expression and this other expression. At the next layer, we actually change abstraction because now we have symmetric bounds, which will give us this expression. And now the output we have now a false alarm, because the lower bound here is 1, and the upper bound here is a bit more than 1, 13, 12. Ugly numbers, sorry, but this is how, this example was built by trial and error. It was a fuzzing, essentially. But now let's look at what the symbolic domain that we have seen already does. We have seen before that this was less precise, okay? Well, in this case, it will not be less precise. We will actually be able to prove the property. Here, we do the radial. We actually, all the radials are undetermined, so we create new expressions already. So you will think we already lost any information that it was useful. But in this case, actually, it's still okay. So here now we have an expression that depends on x10 plus x11. So nothing that relates to the input yet anymore. And here, same, an expression that depends on x10 and x11. And after the random, we have a new symbolic expression that depends on x21. So the next layer, we have something that depends on x10, x11, and x21, which gives us a range, which is 1, 7. And for x31, something that only depends on x21, which gives us a range where the upper bound is smaller than 1. So we can prove the property. And you see, this was the upper bound that we had before with the body, which was worse. The upper bound, the lower bound was the same, but the upper bound was worse. So we managed to prove, to find a better upper bound, even though we lost precision in the way. Actually, we lost precision, but the precision went somewhere where we didn't care about. Because in losing the precision, we actually get a worse upper bound here. With the poly, we got a better one, but that's not what we needed for this particular property. So this allows me to introduce you another trick that we have in absolute interpretation to make domains more precise, which is called the reduced product domain. So essentially, when you have two absolute domains that are not comparable in terms of precision, you can actually combine them together. So essentially, do the analysis with both of them and make them communicate in between to improve the precision. So we can do the same here. We could run in parallel the symbolic and the dipoly domains, and we have them exchange lower and upper bounds to improve their own lower and upper bounds internally. So whatever lower and upper bound dipoly computes will be given to symbolic to make the lower bound and upper bound tighter, and same for the other way around. Let me show you how it works in practice. Here we have to do double work, of course. So we have to do the symbolic abstraction, the dipolar abstraction. We have to maintain the concrete bounds, the numerical bounds. So we have to do all of them at the same time. So the first layer here, what we get is now this range for symbolic, for instance here, this range for dipoly. Now for the symbolic range is better, so we keep that one as a numerical range. Same here for extend. The symbolic range is better, so this is the one that we keep. Next, and the ranges, the numerical ranges are the one that allows us to evaluate whether the value is determined or undetermined, or which abstraction to use with dipoly. Next layer. Here now it's the dipoly range, which is better, 0, 8/3. So this is the one we keep. Here it's the symbolic bound that is better, so this is the one we keep. And after the ReLU, you see now the ReLU, no, it doesn't matter. It's the same ReLU abstraction for dipoly, but now the range is 0, 2 instead of 0, 7/3 as before. And at the end we get these bounds here. So for the X31 we get the same bound as before, as we got with the symbolic. For the upper bound we get something slightly smaller than what we had with dipoly. So combining the two domains together, we actually get something that is more precise than either of one of them. Just a mention of some other methods, you can actually do better. You can even become asymptotically complete. So here, for instance, it's a symbolic domain, but with some input refinement. So let's say you do the symbolic abstraction, you analyze you have your input abstraction. You get an alarm, you cannot prove your property. Well, what you do is that you refine your input and you read the analysis with a smaller input range. And you keep doing that until you actually can find the property to refine. And this is, it works, so it's asymptotically complete with symbolic. You can, every time you do an input refinement, you actually get better bounds in output. It's not true with dipoly. So with dipoly, let's say you have this example here. These are the ranges that you get in output, the ones that we have seen before. Now, if you refine the input, so let's say x00, instead of being between -1 and 1, you make it only go between 0 and 1, well, you actually get a worse upper bound here, which actually, yeah, this is the case that we had before. But if we make the input range larger, we actually get better bounds. This is because of this choice. So in dipoly, there is this choice between the abstractions for the ReLUs. And sometimes with a larger range, you actually get a more favorable choice. So you're not guaranteed to get a more precise abstraction when you refine. Another asymptotically complete method is this one. With dipoly, we have this problem of choosing where to put the lower bound. Here they solve it by putting it roughly parallel to the upper bound, the symbolic upper bound. So they only keep one symbolic lower bound, and it's supposed to minimize the distance. The slope here is supposed to minimize the distance between this line and the actual line of the triangle. And in fact, we can even go further, and we can use a symbolic, optimization techniques to actually find the optimal slope. And this is what the state of the art actually does. They do have, they use some optimization techniques to find the best lower bound, the best slope for the lower bound. And they do this branching, input splitting to find the best output bounds for the network. So there is this annual neural network competition since 2021, and they always win. This is really the state of the art. They have abstractions. This linear approximations, not just for Redus, they have a lot of other activation functions. They support other kind of models. It's just the only disadvantage that I see is that since they use optimization techniques, they actually, when they do this branching bound, they cannot stop in between, in a sense. So either they only do one, they only do this, so one pass. Okay, let me make it clear. Here, with this kind of instructions, you can actually stop whatever you want in the input refiner. You could say, okay, I refine up to a certain point, and then I stop, and it doesn't matter. With the branching bound here, in fact, they cannot. They either have to do branching up to until the end, or they have to stop before doing the branching. So it's not very easy to tweak in a sense. But it does work well in practice. Okay, just a mention of other kind of abstractions. So far we have abstracted the behavior of the model in a sense. There are other approaches that try to compress the models so that we can use the existing verifiers on smaller models that behave in the same way. So for instance, this was one of the first works. I forgot to put you the reference, sorry. I will add it when I correct it. So here, essentially, you have a neural network with some weights on your edges. What they do is basically they merge nodes together, and as a result, they get, now instead of single weights, they get interval weights. And now you can reuse an existing verifier on the smaller models. So you can have your input specification, your output specification. You can use your own verifier as you want, provided it can support interval weights instead of normal weights. As a follow-up, this other paper, here you have the reference. This other paper, they do this compression, but they actually manage to do it in a way that they don't have interval weights. So really now any verifier can actually analyze the compressed model. Good. Okay, the next part will be going into hyper safety properties, still on machine learning. But I will think about it whether later today we do this part first or we do liveness first. I don't know. We have time for questions.